Okay, everyone. So we're back. Before we get started with JAMA, I just want to share a couple of links again. So the first link for JAMA section is here. I'm pasting it in the chat. Um, I also wanted to ask everybody if later on we have a survey to sort of get everybody's where they're at in terms of AI and everything and generically in terms of for science and stuff like that. What are the barriers they face like that? I'd very much appreciate if you at one point could fill out that form afterwards. I'll email to you again because we're using it just for data and to see what people's barriers are. There is a gift card selection if you opt in for that. So far nobody, like there's maybe 3 people who filled out the survey and there's at least 20 gift cards. So the odds aren't 2%, they're much higher than that. You'll get maybe 40-50% chance. But with all that said, I open it up to you, Jama.
Okay, thank you, Amir. Hi everyone. Yeah, my name is Chama. So I think you all have access to this link. Can everyone raise their hand if they have this access to this link? The link that I'm sharing now. Okay, that's nice. Okay, then I'm going directly. So what you do when you're in this link, you just right click, and then you say open in link new tab. This is basically, it will open Colab, and this is exactly what Drew had explained. And then you will see this screen. And another question I want to ask. Okay, great. Okay, that's great. If you so it seems like the link you shared, Amir, is directly to the Google Colab, basically. Okay, okay. Yeah, I want to ask you, how many of you are familiar with AI? Because this will help me to not make a lot of assumptions. How many of you are familiar with AI and machine learning? It doesn't matter. This doesn't assume that you should know, but yeah. Okay. Looks like okay. How many of you are from physics and maths and chemistry? Or
30-40% is about chemistry.
okay.
I
That's
had it in the Google form. The other part is chemical engineering was about 20-30%, and then some electrical, mechanical.
nice.
Yeah.
Nice. So okay.
Don't forget physics. I just want to mention.
Yeah, physics was the other big one.
That's nice. That's nice. Okay. So I'm not physicist, and I'm also not chemist. That's the last time I did was when I was in high school. But I do work about on AI for molecules and things like that, and there is a lot of overlap, chemistry and physics, and also materials. Um, and then okay, so then I will start before I start. So I will start with this picture. So when we talk about AI has a lot of application. You can apply AI to materials, you can apply AI to biology, you can apply AI to anything you could think of. And in our tutorial today, we will go through how can we use AI for materials. And to do that, there are special type of architectures called graph neural networks, which are sort of very suitable. I mean, you could train any AI or machine learning model to do certain tasks, but and graph neural networks have been emerging in this area because of the nature of the data in materials and molecules and biology, which happen to be in graph format. And if you have seen, graphs are used in many places, for example, in social networks, in Google Maps, and in also some of scientific discoveries like, AlphaFold and things like that. They all use some sort of graph representation learning. And if you generally think everything is a graph, if you look at images, text, everything can be represented as a graph. Coming back to molecules or materials, let's say you could have, maybe this is aspirin in 2D. It is the topological graph. which you could represent this in your Python. This is also in 3D, and here is also in 3D geometric graph. You could also represent in Python in suitable data structures, which we will discuss, and also Drew had mentioned some of them. Here they are color. The color is basically is coded based on the features and that that these molecules have. Yeah, for example, black is a carbon, blue is an oxygen, and etc. So then the edges also refer to different types, and we'll discuss that in the later part of the tutorial. So in this tutorial, in short, we'll go through, we'll try to understand the basics of graphs and GNNs. So graphs is a very mathematical, abstract mathematical thing, and people have been studying this in over centuries. Graph neural networks also the same. I mean, neural networks people have been studying, and graph neural networks also have been an area before deep learning that existed. Now people do graph neural networks with deep learning, and that makes it even perform way better. I will go through a bit of geometric because we will use this in this tutorial, but it is just a library that also Drew show how to install, but I will still try to show again. I'm not gonna assume that everyone knows anything here. We will look at how you could load the data, and you could understand your data, and also use data loaders, which I will discuss also. And then we'll implement some graph neural network. A very basic one is, for example, graph convolutional neural networks, which I will also explain what it is. And then we will see some application of these neural networks on some different type of graph, which is not materials, and also some material data set. And this can help you later if you guys have some data set in materials. You could take models of these AI models, especially graph neural networks, to train and predict certain properties in materials. Yeah, at the end, I will give you a short introduction of how you could create your own custom graph dataset. I think biggest challenge is that people not coming from computer science background, they might struggle like, okay, I have this data, how could I transform it to a way that the model can understand, the AI model can understand. And this just becomes a challenge, but I will give you a bit of introduction. It's very easy when you understand, actually. I think there are a lot of things you should basically know before this tutorial, but I think I would not assume anything, but some familiarity with PyTorch is helpful, and I think Drew has touched on this a bit. We will be using PyTorch geometric, and of course PyTorch together. It's also, I mean, very helpful to know a bit of neural network basics. But please, if you don't know what something means, just ask. And I think I have some quick comment to say before I even dive through this. If you don't understand anything, just ask, because you are better off being 5 minutes dumb than being forever dumb. So that's basically, yeah, you are in a situation, if you don't ask, you will forever be dumb. But if you ask, you are just 5 minutes dumb, which is not a shame compared to being forever dumb. So just ask if you don't know. Okay, could you explain to me this in a simple terms? And then I will try to show. At the start of this tutorial and at the end, I share a lot of resources. So think of this tutorial as more of starting like motivation for you, just to see, okay, how could this be applied, how I could use this sort of neural networks for my own research. But this resource I provide with their resources that they also provide, I think you would be in a good place to start, and maybe in your next papers you could use these things. I highly recommend starting with this by Peter. He has a very good theoretical foundational. He has a very good video on explaining foundations of graph neural networks and a lot of examples of it. We're not gonna watch that now, but I think I recommend that you watch that. And if you really like it and you feel like this is something you would like to do in your work, I highly recommend this course from Stanford. They have a lot of different versions. I'm going to zoom it a bit. They have a lot of different versions since they start. So they started this course 2010. Back then, I'm very honest, back then we didn't even know about ChatGPT and these sort of things. And yeah, people were doing still graph neural networks on drug discovery and things like that. And yeah, this is when the course started, but it has a series up to 2023. I like to watch earlier, like somewhere 2020, something like that, because the earlier, the more foundations. Like if the later courses probably will emphasize this new paradigm. AI has changed a lot now with the scaling, so they might add a lot of content of how training a very large, maybe graph neural networks and to do drug discovery and things like that. These are very good, but I think foundations is very important. So maybe somewhere early course which highly focus on foundations may be good, but I didn't watch all of this. My comments might be wrong. Maybe all the materials are almost all the same, but yeah, I really enjoy and I really recommend this one also, this resource. Um, on top of that, I was thinking initially that we would run through together this tutorial and you guys would also run it and then you get to see things. But I'm not sure about the timing. If you really feel like, by the way, you're using Colab Notebook, nothing will happen if you run. Your computer will not crash. So you could just run it. And if you get error, you just come here and you can just restart basically. And so don't be scared. Here are 3 libraries I'm installing, which this Google Colab does not come with. Everything else libraries I'm using already, you have it, Google Colab interestingly installed. Some of them, those I installed. So the ones I install are these. This is already Drew explained to you. This is mainly used for graph neural networks, but there's a lot of other libraries also being used for graph neural, but this is kind of most common one, or the one I use most of the time. This network X is a very good if you just like visualizing things, like just you want to see how graphs look like, how to visualize. I think this is a very good library that helps you visualize your graph. You can create a graph, yeah, let's say simple molecule graph or anything, and you could visualize it. This is not for training neural networks or anything like that, but you could use it for visualizing, or maybe in your paper you could do that. But a lot of people prefer LaTeX because it fits well with research. But yeah, this is a library we'll use maybe at bottom to show you some visualization of how the graphs look like. The last one, and this is an MP API. This API is the one we will use to download some materials data. This is an interesting project I didn't know. I just learned when I was preparing this tutorial because I really don't work on materials, but it's very interesting when I discovered this library, these guys, what they did. It's an API. You can create an account. You get your key. Sorry, that's the key basically. I think we can crop it later, but that's free. I mean, I could even send you my key. You could all use it, but technically you could just log in, and then then you could create your own data and from here. So this has a lot of materials data. So you could see, I will zoom it a bit. In our case, I'm gonna use something in materials that recorded dielectric properties. But yeah, you could create a lot of things with this and your own data set from this. But let's be honest, here just for the tutorial purpose. But and later you could use your own data set. You could have your own local data that you collected in your lab. You could have anything, or maybe already available graph data in materials graph data. And yeah, so that's what this library is about. So we'll be downloading something, and so the problem is that I don't require all of you to run this and also download data and then create the data, all these things. I'm going to show that in the tutorial, but I basically already did this and I saved the data already myself, and I put it in my drive, and you can download it just like this from here. And yeah, we will be using this data to train the model, but I will show you how I did this process basically. This cell is nothing, mostly about just to ignore warnings. I don't recommend you do this in your real work. Maybe it's because certain warnings are very important, but for the purpose of this tutorial, I'm just gonna ignore certain so that we have we can see things clear. This is here we are importing all the libraries that we will use. I will explain most of these while we are using it, but these are some of them. Yeah, I explained. These are NumPy, it's just randomness, torch, network X that I showed you. That I was just showed you. Here is PyTorch. I think Drew touched a bit on torch or what torch provides, but this is you can have your optimizers here when you are training a neural network. I'm gonna run these three. So here, these three are just nothing basically. Here, I'm just importing the libraries we will use, which we will later know what they are about and how we are using it. And here we are setting the seed. So if you guys do research, you will realize that sometimes you would need to set the seed so that you can reproduce your results later on. Until this place, before we go deeper into theory and explaining this material, do you guys have any questions? Or I would assume that everyone understood basically everything. Or everyone, it could be either two cases. Either you understand nothing or you understood everything. So okay, great. I assume that it's either one of the case. Let's assume it's 50-50, okay? So what as I initially mentioned, graphs are very powerful and flexible representation of data. They are used in various areas. For example, social networks, knowledge graphs, recommendation systems, and many other places. In your case, the molecules and materials are also very an area that we use it a lot. So, for example, in material science or crystals or molecules and compounds, these things, for example, the nodes of your graph would represent, for example, atoms, and the edges would correspond to interactions between these atoms. This is an example that it could be in your case. For example, let's say we have this molecule here, or could it be also material? It could be anything. And the way we represent is that we will have this sort of connection in matrices, which tells us how these nodes are connected. Let's say the nodes are your atoms, how they are connected. Here, if you have a blue, which may be equal to 1, that means two nodes are connected. If not, they are not connected, basically. And this is how you could also visualize this graph maybe in a row fashion. So I will explain a bit later, but the nodes and the edges will also correspond to some other features which are related to the graph. Yeah, for example, there are a lot of things you could do with graphs. For example, in chemistry, the graphs are used for drug discovery, to model interactions, or maybe predict the binding affinity. In materials, graphs can represent the crystal structures. They can allow you to predict properties, for example, electrical conductivity, the band gaps, and maybe stability and things like that. In physics, graphs are useful for modeling and atoms or atomic lattices and fluid dynamics or fluid networks, and maybe even energy transfer systems. It's kind of very interesting that a lot of people like these graphs can also appear in many other places. So Sometimes you see images and text. This can also be in graphs, because text is just a line graph, is a graph which is connected sequentially. Images can also be seen as a graph, a grid graph, where there's an equidistance between your nodes or in the graph. Yeah, and this appears many areas. For example, also as I mentioned earlier, like citation networks. Nodes correspond to your papers, and edges would correspond the whole site to whole, basically. Until here, who have any questions before I go to a bit of graphs and networks and go a bit deeper? Does anyone has any question? No. Okay, that's super interesting. Okay, so moving forward, so graph is just an object, so which has vertices here, V, which also can be said nodes in different terminology, and also edges, which are the links or the pairs of U and V, which represent the connections between those nodes. There are then several ways to represent the graph. One way is using an edge list. This is nothing else but is a list of pairs where each pair represents an edge between node of the pair U and to node V. So let's say your pair, you have a node U and you have your node V. Here you have a list of these pairs where each one is the connection from the source to the target kind of thing. Another one I showed in this example, for example, you could represent as edges matrix here, which is a n by n matrix. So you have n nodes, and these are the connections between those nodes. So if the entry of the cell has 1, means there's a connection between those two nodes. If not, there's no connection. You could have also a weighted version of this, where instead of this being 1, you could have some other value, which maybe tells you that the strength of maybe this connection between the two nodes. Another way of representing graph is having an array V, which is unordered list. So here the ith list would correspond to node I. Let's say you have multiple nodes, the ith node, and it would contain all the nodes connected to. So you have the ith element, the index would have all the nodes that are connected to it, basically. In our case, we will use this what we are demonstrating, but I'm going to show you how this looks like in a bit. These are the representation of each one. I think I should have just shown you the example. So here, this is the edge list. So you have node 0 is connected to node 1. As you can see here, 0 is connected to node 1, and 0 is connected to 3. Sorry, 0 is connected to 3. So here, as you can see, I'm going to zoom a bit. This is directed, so it means there's a directional, but 0 it's connected to 3, and 3 is also connected to 0. But you could have a scenario where maybe 0 is not connected to 2, but 2 is actually connected to 0. So this shows you the connection from one to another, basically. This is adjust matrix here is exactly the same thing, but in terms of adjust matrix. And here is the adjust list. So for example, the node index 0 is connected to two nodes, 1 and 3. So 0 is connected to 1 and 3. And that's what basically this shows you. So these are the 3 ways of representing. And yeah, so this is just to describe your graph. This is how you would represent your graph. Here, now we will use the library I was just discussing, Network X, which you could use to visualize a graph. So here, I basically add a graph, the nodes, and I also add the edges manually. So basically, if you create a data set, you would also have to know your nodes and also create your edges and everything, even if someone has not done it for you, basically. So here I have like node 0, 2, 4, 5, 6, and here I have 0 is connected to 2, 0 is connected to 4, 4 is connected to 5, blah, blah, basically. And then yeah, then this G, which is this library, is an object, so it provides a lot of things. So you can easily get the number of nodes, the number of edges, and all those sorts of details. If I run this, I get this graph. As you can see, I'll just take an example. The graph has 5 nodes. So node 0 is connected to 2, for example. So 0 is connected to. In this case, I'd say arithmetic symmetric because this is an undirected graph. Everything is connected to everything, basically. Yeah. So does anyone has question here up to here before I go? So things will get more and more in depth as I go down. So that's why I want everyone to be aligned. And also, if the question is even useless, like you could just ask, like if you don't understand. But I think I would assume that these are mostly basics, and you would maybe that you got almost all of it. But yeah, this is a way of visualizing. So this tool can help you create your own graph and visualize it. You might use it in real world, or you might not use it. But yeah, this is something available to you, basically. Now we will do the similar things with byte geometry, because this is the one that we will use a lot. And this is the library that naturally built for deep learning for graphs. And it handles like it has a way of it creates a data objects and many other and tools and or transformations you could do on graphs. And yeah, so Python geometric, as I said, is just a framework for deep learning on graphs. It has something called a data object, and this data object contains few things. So one thing, it contains data.x. If you access this way, it contains the node feature matrix. So this means every node has some features. So this atom might have these features. Let's say the features of this atom is blah blah, something like, so this mostly should be represented numerically, but in your raw data maybe this would mean something else. So atom would have some maybe textual features or information you collected from the lab. And then yeah, this is where you would store the features of each node. And another thing, this is data.edge index. This is where you store the connectivity between in the graph. So as I mentioned here, edge index basically just tells you how these nodes are connected. Is one representation that I just discussed here. In other words, this tells you how these source nodes are connected to target nodes. So if you have a graph of n by n, how these nodes are connected to the other ones. There are other things you could have. So another thing you could have is edge attribute, which means, so here we had each node we had features, but you could also have every edge you could have also features. So let's say if you have a edge is corresponding to single bond, double bond, and things like that. So and this you could store this information here. So for every edge you would have the corresponding features. Another thing you could train, so let's say you are training a neural network in a supervised way, then you could have maybe the labels. Another thing you could store here is like the positions. So sometimes you are working on positional graph, so where nodes, the exact positions. For example, in the brain, brain is also a neural network, and there are a lot of neurons in the brain, and each neuron might have a position. And for example, in EEG, when we collect data from the brain, what we do, we put some device on your brain. Each electrode, or it would give you data, but then that position is important. So you could also store those sort of information here. This data object, you could store as much information as you would need if you want. That's useful for training your model. Here I'm going to show you a small example. For example, here this I create my edge index. Here's this node is connected to this node is connected to this, blah blah. And here I create X. So for example, my nodes just have a single feature. 0, -1, 0, and 1. And then, yeah, so for example, when I create my data object, you can see X, I have 3 nodes with each one feature of 1, just 1 value. And I have edge index here, which means the connection is 2 by 4. So source to destination. So every node to another node, basically. And for example, edge index 2 by 4 means this you're coming from here and you're going to here. So node 0 is connected to 1 and 1 is connected to 0, etc. basically. And yeah, you can also print things. As I said, you can have access to a lot of attributes basically. So thankfully, Baichi, since it's designed for graphs, it comes with a lot of things like benchmark datasets. For example, Cora dataset, for instance. So for example, here nodes could represent papers. If you have Cora dataset, and edges could represent citations, as I mentioned earlier. And then features could be the word embedding of each paper. So you take the whole text of the paper, and basically you can do one hot encoding, but that would be very large. But you could also use some other model. You could even use GBT models to give you embedding of your text. You could also use like embedding models that already exist. I could share resource for that, but just you could transfer your paper into just a numerical representation, and that would be what your features would be for every node. Here, features means X, by the way. If you think of in the graph and in the data object perspective. Now, yeah, I'm picking here. I'm downloading Cora dataset here. By the way, does anyone has a question before I download this data?
Yeah, so how are the features passed on? They're passed on for every single like node?
Yes, so for every single node, and so let's say here I have 3 nodes and 0, 1, 2, 3, 0, 1, 2, which if we index from 0, so every node here has a feature basically. So every node here would have a feature. Here in my case, for simplicity, I just give a single number basically. But if you, let's say, had atom has a properties, you could use this as a features basically, and you just put it there basically, and you initialize that way, and you can save that data and use it basically.
Okay.
Yeah. Here, I'm gonna automatically take a data set that's already provided to you by BiG. I'm gonna run this, and we're gonna get a lot of details. So it's downloading the data, and then we see a lot of information about this data. So for example, if I print the whole data object, so it contains a lot of information. You could see. So this we have 2,708 nodes in this graph. Each node has a features of size 1,433, and then we have, this is our edge. So we basically have, this is our number of edges we have, and these are the labels. So for every node here, we have a corresponding label, and these two tell you because in this data is already prepared for you for training your neural network. So you could train on this subset of nodes, which is provided to you by this mask. You could then and also validate on this, and at the end you could test your model on this test mask basically. So yeah, so these are the information, the number of nodes, the number of edges, and also the number of classes. So this is something you could easily access from this dataset object. And this is, for example, one dataset. So you would assume if you create your own data, it probably might have some of these and maybe not have some of them, but this is how it should look like somehow. I'm gonna do something interesting. So I'm gonna take, I choose a node, any node, randomly. I mean, I didn't choose randomly here, but I'm just hard coding it. But you could also choose randomly, and then I'm gonna choose all things connected to that. So I'm gonna show you a subset graph connected to this node, so that you could see, for example, how the citation network looks like. And yeah, so if you look at this, is just showing a subset graph. So I choose this node 100, and this node has all this connections. So this is connected to this, and this is connected to everything, all the neighbors. So basically just choose a subset, a subgraph, and using this library network X. So as you can see, this library can help you plot your graphs or do certain things basically. The PyTorch library supports a lot of interesting very important things. For example, it does for you mini patching. So when you train in neural networks, and you can you could train, I mean, with sample by sample, but what we do is mostly when we train a batch is stochastic gradient descent. So it means we train in a patch. So we feed data to the model in a patch, let's say batch of 100, and we update the model, and then we train it that way. And this is a bit less noisier compared to if you use stochastic gradient descent, which just has one sample basically based training. And yeah, what you could see here, like PyTorch geometric already this is basically, you can use PyTorch, you could use anywhere that is data loader. So since PyTorch geometric is based on this, so it automatically supports. So here I just simulate a data set with 4 small graphs, and then I give it to my data loader, and I set my batch size to 2. So so we'll have, when I call this and I iterate through this loader, I will just have a batch of 2 basically. So instead of having 4 graphs, all of them, or instead of having 1 by 1 as if you were iterating, you would have like a patch of like 2, or because I choose patch size of 2. Here, shuffle, what it does, I mean, if you were training this model, you would like to shuffle so that your model doesn't learn a sequence the way the data comes and doesn't become noisy. So you could shuffle this, and this is something important to do when you're training your neural network. I'm just gonna run this. The same thing, you see the same, your batch contains this. I mean, I created, by the way, what I did here is that I created 4 graphs from our dataset, and our dataset was basically our core dataset here. So I just repeated 4 times in other words, and this is written the batch number of nodes and number of edges. So for example, each batch has this number of nodes, number of edges, etc. The PyG also supports a few other things, like transformation. So for example, if you guys worked on, some of you in computer vision, you know that you can transform your images. By the way, there's a question. Could you re-explain what's the input to the GNN? I understand how the graph is come up with the organic molecule, but want each input have. Okay, that's a good question. I'm gonna come to that. There will be like a whole section explaining how we're gonna feed our data to the GNN. And yeah, after we are done with this prior knowledge that we would need, then I will show you that. Good question, and thank you, Maria. And yeah, so for example, if you have computer vision, you could transform your image. Like for example, you could rotate, you could flip, you could do many things. This is just to make your, people say increasing performance, but also to make the model not offer fit to certain structure of the data, but you could, sort of noise in the model, giving different version of the image, and the model should learn somehow. You could do the same thing with graphs, for example. And this PyG transforms supports this kind of things. You could normalize features. So what one thing could happen, you could have your node features maybe different scale. So, and it's good when you're training dynamic neural networks, you might want this to be in the same scale to stabilize your training. And so you normalize your data to some mean and standard deviation. you could add self loops, so you could consider the same node as part of your graph. So the features of that node is considered when you are doing training your model. Yeah, you could convert your graphs to different formats. You could apply augmentation, is anything you think that, for example, a lot of you have a lot of domain knowledge, which this is something maybe interesting you could do with your data, and might even help you get way better performance than someone who doesn't have domain knowledge, like me, for example, in maybe materials. So yeah, so these are, you could do pre-transform, you could do transport dynamically whenever the graph is loaded. These are features that this model supports. For example, here I'm going to show you a simple one. The only thing that changed here, for example, when I was loading this Cora dataset, I just had only this line. I just added one more line here, which is transforms add self loop. By the way, I already imported this as a library up there. That's why some of the things I imported up there are things we are useful. But if you consider where's this T coming from, it's just up there basically in the notebook. And then yeah, I'm just saying that add self loops, and then you could also, the data object thing from PyChi automatically has a function to tell you whether the graph has self loops or not. So let me do that, and you can see, sorry, don't need to save. After you add your self loops, what will happen? You will have new edges created, and then your number of edges will increase compared to what you had before, basically. Something like 1,000 or 10,000, and here you almost have now 13,000, something like that. So your number of edges have increased because you added these self loops. Now I'm going to come even to the part where the graph neural network theory. And before I discuss this, was just wondering if you have any questions. Here we'll discuss how graph neural networks, what they are and how we train them and things like that. And then we'll see the implementation of that. And Amir, you can stop me anytime, and and if you have other plans to say, but I can continue, I think, and from here.
I don't know. Do we want? Is it here to answer Marie Chloe's question?
Is there a different question? I only
No.
the question, Maria's question. I'm gonna answer it. I'm gonna cover much of it, her question,
Okay.
in this section, basically. Okay, so before we answer even Maria's question, I think it's good. Maybe we have a bit of understanding of graph neural network theory. Maybe think of this is your graph. We already looked at what graph is. We know what the edges is, but let's think we have this graph. For example, maybe node A is connected to G, C is connected to A, maybe B is connected to E, or E is connected to F. So let's say you have this graph, okay? The initial, when you prepare your data, it's assumed that you have something like this. So each node here corresponds to some features. Here, I don't have some sort of notation, but you could also have features on each edge here, okay? So this would be the initial representation of each node, but you could have the same for a representation for also the edges. You could have some features here. This is your initial representation. So when before you even think of using graph neural network, you must have this graph where each node has your features, edges might have your features. And then you also need to define what you want to do, the task, where you're trying to predict something, you trying to classify something and things like that. But this is your initial representation. So let's say this is our initial representation. Everyone has this. And then we apply this to GNN. So we feed this to GNN. I'm going to discuss how we dive through this. But let's say this is a black box GNN. We give this GNN, and then GNN gives you a modified representation of each node. So here we had some representation, initial representation, but then every node is updated now after doing something called message passing, done by this graph neural network. and every node gets updated, and then you would have output representations of each node. And once you do that, you train your model, you got new updates of each node, and then you could define some sort of task-specific things on loss. For example, in materials, what we will do down there is like predicting predicting a regression task, which is like the value of dielectric value, basically. And this is basically how it looks like. You have your graph, you feed it to GNN, you get a new representation, you define the task. I'm gonna take example, small example. So I'm gonna take this part of the graph, EDF. So to understand better what this GNN is doing, so we will take this portion of the graph. So let's say here, as I already said, we want to update, our goal is to update this node, because what GNN does, at every node we update this representation. And the way we update, we consider the neighbors, including itself, we consider the neighbors. So here, information come from these two guys and they come to me. And to update this, I need to consider this information coming from these two nodes, okay? So I'm gonna do a bit of notation here. So think of time this T as time step, means the initial representation was time step 1, maybe times with 0 if you index from 0, and then after you apply GNN number of times, your representation basically gets updated every time. So this is your time step, and let's say H here represents your node vector representation. This means every node here has a representation that is H basically. And then K is your edge type. So every edge here might also have features. So in molecules and materials, this could be the bond type. And yeah, so in other areas, it could be something else. But yeah, so this could be the type of edge or any information that could be edge. So then you will have a function. By the way, they will have a function f, which is our neural network function, which basically prepares the message, or in other words, updates your representation. For example, f would, update the representation of D and E for f and for f basically, and then we have U, another important function. I'm going to explain this figure later, but let's keep these notations first. U here means the function that summarizes. So what summarization mean here is that when we have these three nodes, so let's say when we have this node, we summarize information, means that we aggregate information from this node to create information for this node. One message passing information could be here, like summing. You get a new f, the function, you applied your neural network on E, you applied your neural network on D, you get some new representation, and you also applied maybe your neural network on F. Your goal, your aggregation is that maybe sum these two and combine it to F. So that's what you would do here. In other words, is summarizes the received information. And then, I mean, people do different ways, but then you could combine this with three things. So you could combine the previous initial features, could be initial, or it could be the second or previous layer representation of your node, the node you're updating, in our case F. So you combine that with the information from the edge. And when you combine these three, you apply your message passing function, and then you do your summarizing, the function that summarizes this information here. I will also explain how the summarization works in down, but just think of as at the moment how this information is. We are updating a node information by looking at the neighbors and summarizing that for this node. And what you could do now, when you take this and when you summarize this, you could combine this with the node, as I said, mentioned, the node itself, the state of the node. And once you combine the state of the node plus the message, the aggregated message, and then you could apply some sort of non-linearity. I'm not sure if you're familiar with deep learning, but non-linearity here tries to makes in the representation non-linear instead of linear, and I think this is where the most benefit of comes from of training neural networks or deep neural networks. And then you get a new representation for your node, and this is the new representation. So this is how we go from here to get this new representation, basically. Do you have any questions up to this? Could the message take any physical, chemical meaning such as polarization? Exactly. So it can take. I will show in the material section of this tutorial that you could your node information contains exactly what you mentioned, electronegativity and all these things, and it propagates this message basically throughout the network when you're training, and for every node basically. So yes, that's true. And okay, so does anyone have any question in this figure or ambiguous or that couldn't understand? By the way, you can unmute yourself also. You don't necessarily need to chat. Of course, if you are comfortable to chatting, you can also write, but you can also unmute yourself if you prefer not to write.
Jem, I have a question.
So,
what do you mean by the non-linearity? Is this something like kernel or mapping into high dimensions? Is it similar to kernels, or it's something?
This is so one example of non-linearity is this. So I'm going to explain quite simply. So for example, let's say this is a function. Oh.
Some people say.
Sorry. So let's say, if you see on my left side on the screen, let's say you have a relay activation here. This is one non-linearity function that's often used. What it does is that basically, if normally if you don't add this non-linearity, everything will be linear. When you apply your function, if you add this sequential, if you apply this function a couple of times, it's just as if you were applying one. It's because it's just multiplying the you are just transforming your input by multiplying some transformation basically. But when you add non-linearity, it takes to another high dimension. So it transforms from linear to non-linear, and your input it will live in totally different space, embedding space basically.
Okay, great. So it's very similar to kernels, for example, as we use in support vector machines, I would say.
Yes, exactly. So kernel is kernel is basically but kernel is also take your representation, they apply some sort of non-linearity and take it to different. So it's exactly like that, but there's a lot of that. For example, sigmoid is one of them, 10H is one of them, rail is one of them. It's just applies just makes your input non-linear, and actually this is where the most benefit of deep neural network comes from actually.
Okay, just to be clear, you were talking about the activation function, not the data itself.
So this is very good. So activation function here and non-linearity are exactly the same thing basically. So when I say activation function, is a synonym of making non-linearity. So these are, for example, the non-linearity functions, for example, some of them, and these are activation functions also. Yeah. So activation function is actually, I think, a terminology coming from deep learning. I'm not sure, but yeah, this is just the same meaning. It has the same meaning. Maybe.
Okay, does that answer great. Thanks. Yeah, yes. By the way, the channel that you clicked on is the StatQuest channel on YouTube. It's a very good channel to simply learn this kind of stuff.
That's nice. That's nice. Yeah. Just one final point I want to say is that when I say nonlinearity or activation functions here is that if you don't do that, everything becomes linear basically. I don't know how deep I should explain what linear or nonlinear means, but this is something you could check later. But yeah, if like this is your sort of transforming. Think of like you're transforming your input into nonlinear space, basically.
So what is so we are interested in linear problems, but in this case we are transforming our problem from a linear.
The problem, okay, this is a very good question.
Into a nonlinear space, I would say.
So when you have the data doesn't live in a list. So if you have a data, and let's say I would give you maybe a quick example, linear regression here. So so let's say maybe if your data lives like this, so if your data is linear like this, you could just fit a linear line, and you could get a pretty good performance. But imagine you have something like this, nonlinear here. So you cannot fit a linear function on this data, basically, because it's so nonlinear, and you don't know this from the data. So, and then what you should basically do, you should apply a nonlinear function on your data, so that you could have maybe a function that learns something like this. I don't know if you can see what I'm showing. And that's the basic purpose, basically. So everything starts, by the way, from high school. So if you have, this is, for example, like the function, then this is your linear function, basically. But you just put in brackets and applying nonlinearity, basically, the model learns to learn this kind of functions that can fit into this kind of data sets, basically. So when you have your molecules or material data, it might be live in a complicated high dimensional space, and which you cannot fit a function which is just linear. So then that's why you need to apply this sort of activation functions to explore and to introduce nonlinearity, basically. If not, your model would just learn some linear function, and then it might not fit well, basically. That's a bit of maybe neural network basics, but that was a good question. But please ask those kind of questions. I'm also learning from you at the same time.
I don't know. Did we answer Maikoi's second question about the message?
Yeah, we yet to reach that question, because there's another question. This I didn't see. The current dimension is the same idea. Okay, yeah, exactly. Yeah, exactly. Drew also gave a cool answer there. In Mary's question, the second question is answered. Yes, you can have any physical or chemical properties in the nodes on the edges. And yeah, that's the answer. The second question, I think the whole next section is about how we can apply the input to the GNN, basically. I think in a short, when we finish about what GNNs are, we will see a bit of that. Could we feed GNN with nodes as input and do automatic feature engineering? If yes, mostly which algorithm in GNN works for this? Could we feed GNN with nodes as input? Yeah, so basically the graph contains nodes and edges, which edges tell you their connectivity. I'm thinking your question means that maybe you don't have connectivity, you just have nodes. So this is a general paradigm of graphs where you have, for example, they call point clouds, and you don't have any edges, and you just have nodes. And yes, you could fear that people train point clouds. Maybe I could show you that also. And people train this kind of graph neural networks on these kind of things, basically. So if you have this kind of structure, you could indeed feed. So in this case, you will not have the edge index, basically. You just have your nodes, and your neural network learns on these kind of things. And which algorithm to use? There are algorithms exactly for point clouds. You could use any algorithm, even you could use graph convolution, but there are a lot of people working in this area of deep learning, and there's a lot of algorithms. I'm not going to show a specialized algorithm for point clouds, but I could share with you the resources if in case you need. Does that answer your question, Zainab? Okay, nice. Okay. Okay, so we discussed about how this graph neural network works, but there's this stuff maybe we need to understand, task specific and loss and things like that, because most of it comes from here. You would think of, oh, I have this data, but I don't know what to do with it. So, so this is where the task definition means. So you basically need to define the task, and then how, for example, there are three main tasks that you could do with graphs, but I imagine you could also do many other cool things. But this is one thing you could do is like node classification. For example, if your node is a molecule and then you say this molecule has these properties, yes or no, that's just like a binary classification. Another example here, as I given, is that what topic of a paper given a citation network. So you could predict the topic of that paper, basically. Another interesting thing you could do is link prediction or edge prediction. Here is that if like two people are in social network, are they friends or not friends? For example, let's say me and Drew are friends on social network, then Drew knows someone, so the probability that I might be friend with his friend might be high. So you could, predict that. In molecules, you could like predict the bond type. This was a bond, like, or is it double bond, so you could predict the edge type, things related to materials also, and proteins and everything. You could do another thing. You could say you could have a whole graph like this, and then you could predict and like a lot of characteristics. So does, for example, this molecule inhibit some sort of HIV AIDS properties, some diseases or any other thing, or you could predict certain drugs. You could do a lot of things. So these have a lot of tasks. So as I initially showed you here, is that this is your initial input, and then you do your GNN, and then you get a new representation of each node. And then when you get each representation of each node, you could do any task. So if you do node classification, then you just take for each node, you apply some classifier, maybe you get your output is classifier. Here means just a linear function, which basically gives you the classes of that, class probabilities. And then you could compare that against your ground truth labels if you are training in supervised fashion. If not, you could basically you could actually, if not, you could basically train in unsupervised way, but that's totally a different paradigm of AI. But and then you compete the loss, because you're just comparing two things. If they are the same, they're good, you get your loss is good. If not, better. If not, it's miserable. You could do the same thing for this. Is very trick here when you're doing graph classification, but the edges and nodes are kind of the same area. Here, edges, you might need to predict, let's say, take the inner product between the representation of the two nodes. So assume that you have a node here, you have another node here. Each one has a representation. One thing you could do, you could just multiply, take the inner product, or maybe the similarity, and see if these two nodes are connected somehow. And then you could also incorporate this. So you could have some neural network function that gives you this kind of information. But for graph classification, what mostly people do is that you have a representation for each node after you applying GNN. Then they sort of aggregate all that message into aggregate. Here means just taking the mean, for example, or summing all the. Basically, this node has 1, 2, 3. This one has 1, 0, 2. You just add all the information, and you just apply when you aggregate, and then you just apply some function. This is another small neural network, and then you can get your outputs, and then you check against the prediction, the actual ground truth, and that's how you could basically predict. So these are few tasks you could do. Maybe you could do more other tasks. These people do like very cool things. But these are real tasks, and thanks to Peter to provide this. And most of this, I link the resources. You could look at that. I explained this, but I again visualize it in another view. It's again just simply applying the GNN, and then you have new representation, and then you take node classification, and you do like trying to classify what this node properties basically. Before this, we start. So here, everything I think is done with graph neural networks. We'll go through a bit of implementing graph neural networks, a special type of graph neural networks called graph convolutional neural networks, which is one of the early, not very early, but like back in 2010. But I was just wondering if you guys have questions. Would be nice if would be nice, and now it would be a good time to ask. Yeah, if not, we can basically explain this, how to implement this, and then we will train some models. You would see the results and performance, and yeah. Okay. Yeah, nice answers from Drew. I think he can, yeah, you can read if you need those answers also. Now, implementing graph neurons, I will show here in a very simple way. Thankfully, this PyChi or a lot of other libraries, I mean, some other libraries also provide this. It's kind of easy, but I will just touch a bit of what graph convolution is. So graph convolutional neural network just basically does that. Okay, okay, sorry. So what it does is that it computes, this is H. H here means, as I said before, is a new representation of each node here. So every node would have a new representation. And you apply, this is the nonlinearity we discussed, which does transform things from linear to nonlinear. And we have this D, which corresponds to the degree. So this is something I did not mention, but the degree of a node. So for example, this node has a degree of 2. That means this node there are 2 nodes connected to this node. So this contains the information. So it's a matrix, it's a diagonal matrix where every element in the diagonal tells you the connection and between these two, the nodes that are connected to this node, basically. Here is our A, which is our just matrix. So this means how the nodes are connected. So if it's 1, means the 2 nodes are connected. If not 0, it's not connected. You could also have a value there other than 1. Here's the initial representation of the nodes. As I said, so you have the initial node representation of each, so the atom's initial features. And then this is the linear thing that I think Drew showed you already. So this is basically applying a linear function. Is basically on this. But this linear is like in PyTorch, it's just like NN dot linear, but it's just think of multiplying some learnable matrix to your input, basically. And this up to here, everything is linear, but then when you apply this, everything becomes nonlinear. Another thing I need to mention, this diagonal matrix is a symmetric, so Dij is equal to Dji. And if we zoom a bit for one particular node, this is what's happening basically. This is exactly how you would write mathematically whatever we explain visually here, like exactly the same thing but in a mathematical form. Here we apply every, so this J means the neighbors of I. So let's say we are updating node I. This is every neighbor of J is every neighbor of I. And then we are summing, this is your aggregation function, the U thing we were discussing. What we do, we apply a function here, function applying F means here just applying linear function to your input representation J. So to every neighbor, you take every neighbor. So for example, here, your neighbors were what? Where's our cool image? Oh, something disappeared. Oh yeah, this is image. So our neighbors here are E and D, so I think of that J here is just 2 E and D. So you apply your linear function to every neighbor. This W transforms your J, so your Chaitin neighbor representation, and then you sum all of them, and then you normalize, and then you apply your nonlinearity. So once you do this, then you get a new representation of this node. So this is just a matrix form, but for all nodes, but this is also doing it in a basic way and representation. So this corresponds to the same thing, but this is just for one node. Do you have any question about these figures and also how this is done mathematically? But basically, if you were to implement from scratch, this is how you would do things. But thankfully, we don't need to do that. Because I mean, there are libraries like Pythogeometric. I will maybe show you quickly what Pythogeometric here is. In Pythogeometric, you could look at the documentation in your own free time. But this is, they provide almost everything here, from data to loader to sampler. They provide everything here. You could even go to their introduction by example. They even have some cool visualization. And they also have, some already implemented neural networks here. For example, our case, the one I'm explaining is, if you look at convolutional networks, I think it's this one. So I was just basically explaining this here. Instead of W, they have theta here. This is basically showing what I was just trying to show. So they basically, you have this implemented for you. So you just need to call this one, for example, and you don't need to implement it yourself. But if you are just curious or for learning purpose, you could do it. But I think as you guys working on domain, I think you might not have the time to do that. So you can just use the library, assuming that you really understood what the library is doing. One thing you could do here, if you look at, we just normalize this by the degree, not degrees. But since it is symmetric, one thing the authors of this paper do, they add symmetric normalization. And so instead of just doing this, they multiply this and this from this side, which mathematically means, and if you look at Zoom, I think this guy write it better. If you look at for every node, this is exactly what this means, dj and di. So basically, dj and di here would mean the in degree and the out degree. And the fact that now it's symmetric, so it's technically the same, you just multiplying the same number, basically. And after you do that, if you do this symmetric normalization, then you have your new H like this. And then that's it. That's graph convolution network, maybe in a small introduction. This is this particular graph neural network that you could use to do your anything that you would want. Do you have any questions here? Okay. What if the message we want to pass is external or conditional? Example, presence of an electric field, solvation. Interesting.
I think that's maybe in Mehdi's domain.
would be
so if you did solvation, you'd have you could have an explicit solvation model, but in that case you just have more molecules around your core focus molecules. So that wouldn't be a big thing. If you used what's not explicit, implicit continuum models, I don't know if it's ever been done. I don't think I've ever seen something like that, actually. Mehdi?
That's a very interesting question. Mary, can you explain? My understanding of this question is this. It's like my understanding, Mary, correcting me. You mean that, how about if I don't want condition this, what message I pass to F, right? Like you constrain what goes to F basically during message passing. Is that your question, by the way? And if that's your question, yes, it's doable. People do that. You could condition, for example, a simplistic way is that you could block the edge and not pass anything to F, but you could also do some conditions that, do the message passing. That would require you to do some update if you are using the library, but if you are implementing from scratch, it's something you could do, and people indeed do that. But I'm not sure if that was your question. Maybe Amir has answered better.
I think if you had an electric field,
Mhm.
like you could say, what is the strength of the electric field? I think acting on every atom, and you would put that value in the feature of with the node.
Yes.
So that would be, I think, one way to
Mhm.
convey, provide that information to the system about the presence of an electric field. I think the same could probably be said for like a continuum implicit solvation model. But until I see a proper paper to see like good methodology, I wouldn't quote myself. Because the majority of the papers right now are just they're generating, they're generating all these new materials, but it's just like it's a solid state material. It's a slab of this, it's a slab of that, it's a 2D material. There are some absorption papers using graph neural networks, but I haven't seen anybody push um, absorption in a solvation model for graph neural networks. I'll be 100% honest.
Interesting.
So I'll share my opinion as well. So the presence of electric field or solvation will directly affect the geometry of the molecule, for example, and how it translates. Again, it would be on the edge features. For example, it affects the bond length, or it will be translated into the node features. And this could be achieved by just, again, so these are the effects on the geometry, presence of the electric field and the solvation. And you can encode this electric field or solvation by, correct me, Gemma, by one hot coding. So if there is a solvation model, it will be 1. If there is no solvation, it will be 0 in the feature again.
Okay. Nice. I think I understand the question better now. Go ahead, Duru. You want to say something?
Yeah, I started typing, but I'll just speak out loud because it'll be faster. So in my little extension to your reply earlier, I mentioned that we have this mapping from some concrete features of, say, your features about the atoms, right? Or components of molecules, whatever level you're describing your nodes at. But that mapping function could take in more global features as well, right? So like Amir said, you can take in the intensity of the ambient electric field, right? You can also, because you could also take in some additional embedding of the medium that your molecule is in as well. And that's the power of working in these learned embedding spaces, is that you, in the end, the way often these issues are addressed is you have one vector representing the node itself, so the atom, for example, and its properties, and you have another vector representing the ambient conditions, and you sum them together. And I don't know that this is exactly how it would be applied in material sciences. But when we have those kinds of, we have two distinct concepts and we want to somehow fuse them, if both concepts are learned, you can literally just add the vectors together. And the model will learn how to integrate the information.
Okay, I shared a article, a published molecule, skimming down to the methodology. They say they did the, I think, molecular dynamics for solvation. They say the snapshots serve as starting coordinates for new simulation of 200 picoseconds length, where the solute was positionally restrained. For each solute atom, the forces exerted by the solvent on the solute were averaged. So I guess, yeah, like sort of like Mehdi said, the effect of the solvent is recorded in the forces, and then you have a forces acting on each atom. So that's one way to incorporate that information by the looks of it. But this was for molecular dynamics. I don't know if your field might be more density functional theory. That's probably more rigorous. But it is being done by the looks of it. We'll try and remember this question for our second, our part 2 of our event. That I think our speaker for that might have done this or something like that. But this was a good question. Thank you.
Thank you, Mari. That's a very good question. But yeah, so as Drew said, you could always incorporate your features here, whatever you have. You could have extra global features and things like that, and you could always, train it with your neural network. Okay, let us move forward if there is no any other question. Okay, that's good. So to implement this graph, this graph convolutional neural network I just explained, it's already provided to you, thankfully, as I just showed you from the documentation here. We already imported this up there in the notebook. So you just define. So for example, this is one layer, message passing, and then another GNN layer. So this is basically just having 2 layers, and this means we update each node and by layer 1 and then layer 2. And then so what you do basically, if you're trying to write this kind of neural network, you define your layers here, or your graph neural network layers, and then you basically, I'm extracting here the edge index, which tells me the connections of how the nodes are connected, and this is my node features. So this is a very simple case. And then I apply, for example, the first layer, then I get a new representation of my input. So X at this point is initial representation that you prepared when you prepared the data. And then you apply your graph neural network, you apply your nonlinearity, which I will explain. And, if this was not there, it would be just like as if you were doing just one layer of neural network. So then you will have your second layer, and then after this we apply softmax. I'm not sure I did explain this, but this sort of converts your outputs into probability so that you can do classification. Sorry for making a lot of assumptions here, but I mean, these details are things we could also go through later. For example, what does this touch NN.module means? Some of them Drew has explained already. But this is how you would write your small model, basically, in graph neural network. You feed your data. This is how you give your data. This libraries already support. I already showed you how this data is created. You could access these things easily. And this is basically your model. And now what we will do, maybe we'll use this model to train, we'll read our core dataset. This is our citation network dataset. And this dataset contains this number of classes we can extract from there. This 16 basically means, so this W here, the linear layer here. So inside here, if you look at the documentation, they have this linear layer, which is just the theta function or the W function I explained earlier. This is basically the number of hidden dimensions that function has, basically. So 16 means that, let's say if my input features was, let's say 32, then it would project the transformation W theta will project to 16, basically. So it's just multiplying matrices, basically. And then then your output feature dimension would be 16. So that's it. And then you initialize your model here. You also have to tell your model what are your input feature dimensions, and that's it. And then you define your model. When you define your model, then you could, this is a very simple, like very simplistic training loop. Training loop just means that you just train your model using stochastic gradient descent, and update your neural network. So basically, it's the whole process of doing the back propagation and updating your neural network. And I think when you go through the neural network basics, you will understand what this training loop means in depth. But let's say we are training here, we are just teaching the model to learn our data. And how did we, this is coming back to make it very clear what Mario was asking, how do you feed your data to this? So yeah, this is how you feed our data basically. So we call the model, we initialize our model up here, and we also initialized our data here. This is our data set. And another thing we do is that, so I call this train function because my data set is just a single graph, because the citation network, we care about the nodes. I just feed the whole data as it is. And I train the model, but in certain cases you might have, you might be training, in batch wise, and you can have your train loader and something like that, instead of just, training your model like this. But there are different ways of writing your training loop, but just think of that this is a way of teaching your model. Someone was unmuted, probably wanted to ask a question, or maybe not. But yeah, so you train your model, so you retrieve your train mask, so provides the nodes that you are training your model on. So we don't want to train your model almost all nodes. We need to leave some nodes for maybe validation or testing or something like that. And here we retrieve the nodes that only correspond to this train to the train mask, so the nodes for training. And yeah, here what we call normally, this is what forward propagation means. It's like we feed your model, your data to the model, and then you compute your loss, and then you do the backward propagation, which is another to update your basically gradients of your model. And then you optimize here. This optimizer step just optimizes your parameters and update your model parameters basically. And then you can return your loss. Let's train and then see. And as you can see, if your model is learning, you should see your loss going down, and most likely, I mean, if not, it means there's an issue. If it's increasing your loss, then it's actually an issue, unless you are maximizing instead of minimizing. But yeah, that's the case. And then so for example, it looks like this model is learning quite well. Now we have another test function which just uses the test data set and computes the accuracy. And yeah, I've already run this, but you could see that this model gets this about IT accuracy on this data set. And yeah, if you look at it here, we just train a very simple 2-layer GCN model, and we could get about 80% accuracy. Just want to come back, emphasize here, Maria, is it clear now how you would feed your data to the model? Or should I clarify a bit more, or is everyone clear how you would feed maybe small data to your neural network, basically? Of course, there are things that I did not explain well, but I assume that these things something you would cover later, like mostly what these functions are doing, the backward optimizer step, explain what's happening in the forward. Maybe this line computes the loss, but maybe you need to understand this negative likelihood loss. This just to things that I think we would need another tutorial if we. Okay, she asked clarify the transform. And are you referring that how this model transforms your input? Is that okay? Is that the question? So I mean, let me I'm not sure what transform mean here, but if I understood, is that how this graph convolution would transfer your input? So yeah, is that the question? If that's the question, yeah, what it does is basically exactly these things I explained here. The transformation that's happening in the forward is basically taking the initial. Sorry, it's just how I get the same dimension for the input. Yes, so the dimension. So let's say you have an initial dimension of your input, and maybe I could give a quick example. I already given here. Like I will try to emphasize. So let's say your input had this, or maybe using this data set, we had 2,708 nodes, and each one had a dimension. Each feature had this. This is the embedding dimension or the features of your nodes, and we gave what we did here. We provided our model what that is. So here, when we call it, we provided the number of features each node has. And when we initialize our graph convolution, we tell directly this number of features as your input channels. And this Hindle channel is basically projects this number of features. Let's say what we had 1,400 and something, it will project to 16. So it is just a linear transformation, transforms from this 100 something to another dimension of 16. That is how your shape is behaving. Yeah. So basically, you don't need to keep the same shape throughout your network. I mean, once you project it, the second layer would just take the projected dimension as an input, and then it will again project it to our output dimension. So here I'm already saying I'm done. So I will say I will project it to output channels. Output channels here, it will be, if I'm doing classification here, will be the number of classes basically. So this, I'm projecting my 16 to 10, for example, if I have 10 classes here. And then, so that is, in this case, we have 7 classes. So this number will be 7. And this last guy will basically return something of x to 7, basically. And then you could do that, basically, yeah. And then you can apply softmax to convert the probabilities. And okay, great. And yeah, this is the training loop, and that's it. I'm wondering if there are other questions, because now we're gonna go a bit of an engineering of how you would create your custom materials data set, and then yeah, after this, then we'll show training model on this materials data set. Yeah, so if you have any questions, would be okay. If not, we can continue basically. Okay, I want to ask a question. How many of you understand nothing? It's not bad. Like I have been in a situation where I got nothing from from a whole lecture, and I just feel like, so how many of you got like nothing maybe?
Well, so I've already trained a ML. I've trained a SVR, linear regression. So, the formatting of the X dot for the inputs, like that I've already seen. So I know the setup is I guess it's well standardized between all these packages. I had used scikit-learn, but that was mainly the same. I mean, in terms of, the mathematics, I just look at this and like, it's a lot of matrix operations that are happening on the back end. I know there's an activation function. I know we want to make it non-linear because it helps the data. It's just better for it to be. You're able to look at trends that maybe wouldn't be seeable by the system, by the computer, if it was linear. So it's a conceptual understanding. I'm not going to say, I'm never going to have to pass your comprehensive exam, Jama. So that's the way I look at it, and as chemists and majority here, I think our chemistry materials background, that's, I don't expect or desire, I'll be honest, I don't desire to learn it, to know it to the level you have, I know, but somebody on my papers will be computer scientist, or somebody on the team will be computer scientist, so they can answer this question. But I follow the process. I know the activation function, everything. I think it's happening in the model.train step, and when you say model data, that's when it's maybe applying all the matrix operations and the activation function. That's what I understood on. Yeah,
that's nice. I think as Drew said, would be the section 6 would be the most interesting part to many of you. Maybe the one you want. So technically you would want to create this sort of data, I mean any data, and then you would just train this model. I really don't expect someone to really have in-depth theoretical knowledge in this. Even me, sometimes I make mistakes and I have to review the documentation of the paper to understand better. Yeah, there's no expectation there. Yeah, I think think this section would be an interesting, and it's also not that long, so I think we would have more. I would probably then also need more of your help here, because there are a lot of domain things we will discuss here. But yeah, let's if no one has a question, then we can just discuss how you could create your materials dataset and how you could train a model on this dataset, for example. I'm not going to run some of the cells here because I have to provide my API and do it. I could do that, but it sometimes takes time to send a request to the API, and while you're downloading the data. I'm just going to show through how the process is done, basically. Okay, nice. Yeah, it's good that you send this resource, because I cannot send it. Okay, so this guys, as I showed you here, they provide a lot of materials data, and technically I'm using this, but I assume that many of you already have access to these things. So what we will do here is that we will just download the data from there and construct the data from raw, basically. In here, our nodes would represent atoms with features such as atomic number, mass, atomic mass, melting point, electronegativity, etc. So nodes could represent anything, and I would show you how that you could do that. And then your edges could represent bond strength and distance and anything you would like it to represent. And then you would have your graph targets, which correspond here. Targets means your labels or your ground truth targets. In the case here, what I do is this dielectric constant. This is what we are basically predicting. Then using this data set, we'll train a graph convolutional neural network, which is the model which I just explained, then to predict these dielectric constants. I wonder if is it something very interesting to use dielectric in materials? I'm just wondering how. I'm not sure, but if one of you or Amir or Mehdi could comment on like where this is used, maybe applications or something like that, and just for the audience, if needed.
I think for batteries, it's proportional to like electrical conductivity. So a higher constant, I think, will mean better conductivity.
Amazing. Amazing. That's a very good context, I think, is someone to have. Okay, so now this next section will basically download this data from materials project API, which I just showed. What will fetch about 600 materials which have recorded dielectric properties, and each one will contain this and of course some other things. But what we'll have the material ID, we'll have the crystal structure, which contains all the information like atomic positions, lattice, connectivity, and everything. And then it will also have this dielectric constant, which measures the material, how material interacts with the electric fields. So I'm not going to run this because, I mean, I don't want to send a bad request this now and run, but this is when I run, and it should run for you. You can create your account easily in this repo. You can create your own account, and then you should be able to basically download it. And it's free, so in any API you get it should work for you, and I think thanks to them. But yeah, let's say this is just, these lines are just nothing. This call is, I think Drew explained what with means, but this is basically open this as an NPR, and then you try to take material 600 materials 6 times 100, so we're going to fetch 100 at a time, and we will need chunks of SIGs. And what we will do, someone asked why emmet library we're using. It just helps us to filter out things because we're taking this has property. So we want something that only has dielectric properties, basically. So we'll not download anything. So at the end, our data will contain this material ID, the structure, the dielectric, and yeah, that's it. Now, once we download this data is raw. We have basically, it's not a graph. Now we will convert this to graph. We're going to use this function, the function here, which is get atomic features. And this function basically creates our node features. So a lot of you asked like what our nodes could be. So here, for example, each node here we provide, each node will have these features, for example, like atomic number, atomic mass, ionization, and it could have many things, like you could put any number there. So each one here could correspond to a number. Could be your actual features. So for that node, basically, or for that atom. And yeah, so basically, so this is how you would construct your node features from that very raw data. I'm sure you guys would probably do it in totally different way, but this is how you would do that. And now we will build our graph. So to build our graph, we need two things. Keep in mind, we need the node features, and we also need the edge index. I think the most important is the connectivity. I mean, unless you want something that has no connectivity, which is independent thing, but you need the connectivity, and these are the two things we care about. So the node features, so we take every side from our structure, and then we extract the species of that side, and then we give it to this. So then what happens is basically this. So here we create all our nodes, basically. So here we will have all the nodes. So in our case, let's say 600, basically. And we create the node features by calling this function, basically. And each node would then correspond to the features we just discussed recently, which is just, this information. So now we create every node, and we create every node, and there is corresponding features, basically. So you would have your node features here. So let's say you have 10 nodes, and each one would have these features. So thankfully, this API automatically provides to you to get this structure. And then, yeah, you can basically extract all the information you need from this structure, basically. I was looking at the structure, so you could go to the documentation and see what other things you could get from the structure, but there's a lot of things. So if you look at this, they have almost a lot of things. Some of them I'm not even familiar with, but yeah, you could extract as many things as you want, and you could also add your own domain knowledge features, basically. Now, after this, then you construct edges. So you could construct edges. So you could also incorporate here your domain knowledge if you want. In this case, what I do is basically you get something called, we use this library called crystal NN. Basically, it does the nearest neighbor thing. It looks at it extracts the nearest neighbors. So given you give the structure, and it will extract the neighbors of every node, basically. So every node I, it will give you the corresponding neighbors. And then for every neighbor, what basically I do is you take the neighbor itself, you get the weight. For example, let's say here you could have the bond strength or your distance or things like that. And then another information that the edge. So these are the features that you could go to your edge, basically. So you could have this weight as a feature in your edge. You could also have another feature here. I just put distance, which just combines the distance between the coordinates. But you could also add other features here. And all these features you see, I added to this edge attribute, means I consider for every edge, I will need to have this weight, edge, and then you could have more of that. And then you would also need to create in your edge index, you need to create this edge list thing we discussed, which basically corresponds node I is connected to node J. And then here I basically convert that to a tensor in PyTorch. And we also create here our label. and our label, which comes from the dielectric, which is automatically given. So for every structure, we have the corresponding dielectric constant value, basically. And when you have that, then you can basically put all this information to the byte data object, your node features, your edge index, your edge attribute, and everything. And then you could also put your labels, and then that's your graph data. This is very important cell, but do you guys have any questions? And I feel like I cover a lot, but basically what we did at the end is not that, really, I think the most interesting here is how you create your node features here, this cell, which this function does. And the edges are basically, you can, in this case, I just use nearest neighbors, but you could use any other thing. Like, I'm not sure how certain materials are connected, but you could have some sort of other way of inferring the connections between your atoms, basically, and maybe from the law.
So this, everything you wrote here, this comes from PyMatGen's documentation, or this
No,
is?
oh no, this is from scratch. But what we are using certain tools from PyMatGen. For example, this crystal neural.
Okay.
To get the neighbors. What else are we using? I think that's it. The rest, and we are also using this element, so which basically is interesting, right? This element gives you it's like a periodic table in high school, basically.
Yeah.
So basically,
people definitely made these packages. The scientific community has done a lot of it.
Yeah,
the hard part is when it's not all in one location. The text, you have to go to all these different packages back and forth, and then your efficiency just drops. So I wasn't sure if you had found it through Crystal. Okay, no, I just also you mentioned Crystal NNN. Many, what other ones we've seen? We've seen the first, I think the oldest one was for materials was called CGNN or Crystal. I know there were so many that came out, and so I know Crystal NNN I didn't hear of, but there was one, I think one of the old ones from a physicist in around 2016. It was called CGCNN or something like that. But of course, I don't think how the other models, they might have different setup. So the intricacies of how you feed it the data would be slightly different. So I don't know if it would I don't think you can just change the name of the model and it'll package it for you the same way. You might have to play around with it more.
Exactly. So
this Crystal NN was just to determine the neighbors around each atom in the structure.
So you could
okay.
Yes, so when you download, when you get your structures from the materials project, you can loop through each element in that structure. It gives us the unit cell. So if a unit cell has 2 atoms, it will go through atom number 1. And what Gemma did in that beautiful cell is that he requested the element function from PyMatGen. So it will recognize the element and just gives us the intrinsic properties of that element. In the first step, those are our node features. And it will go to the next atom. And again, it recognizes what element is that. It will give us the node features again. So we have 2 atoms, 2 nodes, and each node has its own features, if I'm correct.
Exactly.
So the previous cell takes care of the nodes, but what is tricky here exactly? The upper cell. Yes, but what is important? Yes, this cell takes care of the nodes and the nodes feature. But what is very confusing and challenging is the bonds between atoms.
Exactly.
So sometimes you have a complicated structure. They have different. There is more atoms in the unit cell, so you have to loop through each atom, get the neighbors, make sure that you're not double counting, and then return the features. So that heavily relies on your coding ability here. There is, I would say, no magic, as Gemma mentioned. Everything is from scratch.
Exactly. That's basically exactly as you said, Mehdi. Thank you very much, by the way. That's very good explanation and also answer or simplify things. So yeah, this basically few lines are really not magic. You could do in many ways. I actually saw that even by matching, they also automatically provide some another way of getting neighbors. I don't know what they return the whole neighbor. So definitely this neighbor is an object and contains many other things like the weight and things like that. If it came within, if the structure had a weight also. So yeah, I think that's it and how you do that. And here you could just run this for all your basically material. So every material ID, you take it and you just call it convert to a graph, and yeah, that's how you create a whole graph dataset. So this is more like a graph level task, and then you don't need to run this cell unless you run these cells before. This cell just shows you how you save this to PyTorch data. But yeah, but in our case, we will just load it. I already did this process. I'm just gonna load it for you. I already saved the 600 materials. I converted to graphs. I save it into a file. I have the file downloaded initially when we started the tutorial. Then you could just load it. You can see your graph, for example, here. Interestingly, you can see, so we have 16 nodes. I just picked the first graph. Basically, you have 16 nodes. Each node has 14 features. You have 16 edges. You have each edge, 16 edges has a feature of 2. This basically corresponds to the distance and the weight. And yeah, and then you have the corresponding label, basically. You could actually extract further. You could just do this to get what the label is. So here's the dielectric constant is 1.2 something, basically. So we will train a model for an unseen graph. Can we predict basically this value? That's what we will basically do, basically. And now, yeah, so another machine learning thing, which is also not magic, is that when you're training, like for example, when I was training Cora dataset, they already provided you, because it was node level task, they provided you the masking which nodes to train on, which nodes not to train on. Here we're doing graph level. You can simply use train test split from scikit-learn and just split our data into train and test, and that's what we'll do here. We'll have 480 for training and 120 for testing, basically. Once we do that, now we'll do like a neural network, but our neural network will be a bit different. So remember when we train node level data. So the difference is very minor. I just want to show you. You will always have to modify very simple thing. When we were doing a simple node level task classification, we just had this. We just have 2 layers of graph convolution. We extracted the node features and the connections, whatever the edge index from this data, from our data, and then we feed it to our graph convolutional neural network. We applied nonlinearity, and then we did these basic steps, right? The only difference you will see in this neural network is because the task changed. So when the task changed, we'll need to do minor things. So we are doing, first of all, a graph level task. So since we're doing graph level task, we need to aggregate information or some sort of the information from all the nodes into one representation. And then the second thing that changed here before aggregation, we also have another line, which is a linear, fully connected network, a symbol function, which basically projects the representation of the graph into one, because we just care, like we are predicting a continuous value. We're doing a regression task, and we just want to predict the one particular value instead of doing classification of classifying multiple classes. So these are the only difference now. So you could see basically we have everything in the same. So we have the same graph, layers, and the only thing we added is just to adapt to new task. For example, now we're doing graph level task, and then we just do this aggregation and then this fully connected network, basically. And then now here in your patch size, every symbol you have will have a value which is something dielectric value, basically, that the model learn and predicted. I'm gonna run that, but that's the only difference. If you have any questions with these lines, these two lines, if you don't have any questions, we can just train this model and then see the performance. And here, since we are doing, regression, we will use mean square error loss, and that's how we will train. Let me just quickly train that. We just do the same similar initialization. By the way, here there is a question. Imagine, if you remember, in the other data set, what we did, we extracted the input channel is the data automatically came with. In this case, our input feature is the dimension, it's X of the second dimension, basically. So that's how what my input channels would be, and my hidden dimension would be anything I would like, basically. Anything I would like to project my my input. Then we will train this. Yeah, as you can see, the loss is extremely high, and then it tries to go down as you train it. And yeah, we normally expect this to behave this way, unless there are some bugs or maybe some theoretical bugs, which also could happen. And lastly, we can compute this on the test data set, because we split our data into train and validation or test, and then we have this. I think we are finished with the tutorial. Before I go to the last section, which is gives you a very final keynotes. Do you guys have any questions on anything for this? I'm sure this is very long, and probably a lot of you might have just slept.
So, okay, I know the earlier model you had, it was very simple, just like 2 layers, right?
Yes.
So this one here, the GCN regressor, you fed it 16 hidden channels. If I wanted to make sure it's the absolute best, I would have to almost iteratively change 16 to various numbers to find the best one, right?
Yes.
Okay.
This is for simplicity, just use 16, but you could always, have any number. Just make sure you have the computational resources of whatever you do, but exactly, you could.
And the atom optimizer,
oh, that's a good question.
I just what is it optimizing? Because I thought it would optimize the hidden channels for us, but I don't think it's doing that. So I guess the loss function, I guess.
So there is something called gradient descent. Maybe I have to start from there before I go on it in there. So gradient descent, what it does is, you're training a model, passing, you train a model and you want your loss to go all the way down. I'm going to give a this could be a whole another lecture, but I'm going to give a very quick introduction. But assume that we want our loss to go to this minimum position. We're training like this, and this is what gradient descent does. So takes a sample, gives it updates with the model, and then it computes the loss, and then we expect the loss to go down. Now, there is a special in kind of gradient descent called stochastic gradient descent, which does bare sample wise and update of, so this update, instead of having it's happening every sample. So you feed it, you just give one sample, and there's another patch, stochastic gradient descent, which you give a patch to your model and it does updates. So Adam is a special kind of optimizer. So this stochastic gradient descent is actually an optimizer, and that's what optimizer means here, is just to update your model parameters so that we can reach the global minimum or local minimum, where global minimum, local minimum is like reducing your loss in this sort of curve. So what Adam is a special type of optimizer, and so if you look at this stochastic gradient descent, so Adam is proposed in this paper. So it's a special type of optimizer. It does this very minor thing, but this is gonna go too technical, but it just has it does the update in a different way. So it has some other variables like beta and things like that, and it multiplies some constants, and it's known to be it's widely used, Adam, basically, but it's just a stochastic gradient descent, a modified version of stochastic gradient descent, where the update role is a bit different because you are learning some constants. There are some constants in this. So I can send you the formula for that, what Adam means. I don't know how to send it, but it's an optimizer.
Yeah.
And
Yeah, no, I've seen it a lot. I think the inventor has won quite a few prizes for his work on that.
Yes. Yeah, but yeah, and there are a lot of them. There is another different types of optimizers, which are also, Adam W, which has a weight decay. So these are a lot of deep learning, ways of doing it. So there are different, so just think, so when you're training your neural network, you need your optimizer, you need your model, you need your loss function, and yeah, those are very important. Those are three things you need, and you need your data, of course. So those are three things you need, basically. So once you, the conv1 and conv2 and fully connected layers, all parameter weights like this. Adam's finding the weights. Yeah, exactly. Yeah. So yeah, I think if there is no other question, what I would suggest here, like some sort of take-home assignment, I think the best thing to do now would be maybe convert this into an edge problem. So instead of doing things with nodes or graphs, so we did what node level, we did graph level task, maybe do something with edge. So can you predict properties of the edges? In that case, what you would have basically, you would exactly have this. So you see, you will still have this thing, but you would maybe split your data in terms of, you will do some sort of masking, and you'll train some edges, and your label will be maybe the weight or the distance, or maybe the bond type, edge type is the 1, 2, 3, 0. And then you could, you could then, validate that on another mask, which is independent data. And that's something you could do, and I think could be a good exercise. And if some of you are interested more of connections between materials, and that would be a good task to do. And there's a lot of tutorials and open source material and how to do this. Another thing is that everything now we discussed, we just did a very simple data sets, like a data set which you could even load into our memory. But it might be the case that this is not the case. So if you are training for extremely large materials data set on using graph representation learning, what you might need to do is that you might not even use data objective or whatever we did Baichi. I mean, you might use Baichi to some extent, maybe to define your layers or anything, but your data might be in a totally different object. So you could be stored here. These are different ways of storing large data sets. Instead, for example, I store in my case in .pt because it's very small to load all of the data into memory. But you could still store in .pt, but you would have to then have your own custom data loader, and which sort of gives you your batch or your samples and reading it from memory, but not from the RAM, basically. And I think this could be something you could try. I mean, it's doable. And I think if you do this too, I'm sure, I think there's nothing much else you would need just to train graph neural networks. Another recommendation I have, I think, which this lecture didn't cover much, is that anything related to optimizer or deep neural network basics, or maybe back propagation, or how these things happen, I think would be nice. Maybe if you take some other course that explains what these are, because you could get a lot of issues when training your models, and most of the time these issues could come from in these areas. So here, mostly what we discussed was how you could use GNNs for materials, but you would need almost everything. GNN is a special type of neural network, but you need almost all the information, like what's gradient descent, what's stochastic gradient descent, what are other optimizers that exist, and also, yeah, I mean, anything that relates to deep neural network. I mean, what are other graph neural network that you could use also? So yeah, and I think that's our final recommendation. Lastly, this course mostly provides everything. So this is another course. I have been a TA for this course a long time ago. It basically covers everything. It's a geometric deep learning course, and yeah, it's some of the most leading expertise in this field. They teach this course, and it is very interesting. It has the recordings, it has the slides. It might be very tough, I would say. It might, because it requires a lot of theoretical knowledge. But if in that case, I think this is also another one you could take, which is the one I just showed from Stanford. This courses gives you a bit both understanding of deep learning and also graph neural networks. And yeah, and that's it. And there are here, I need to thank these other tutorials, which some of them I created, for taking some of the things that we had in this tutorial. I think that's it from me for today. And thank you so much for everyone. And I hope you enjoyed, and I hope you at least learn 0.01% of everything we covered, because that's useful. At least knowing this is possible, then you can always learn. After this tutorial, you're not expected to know everything, basically. So, and I'm happy to take some questions if the audience have questions, or anyone else. But yeah, that's it.
Okay, nobody's saying anything, but I think I'll just add. I know we did it on materials and materials project. I used my API; it did work. All the code. Some of you might be more into other just pure chemistry. We almost had done other data sets like QM9, which I think were Jama. You said were quite well packaged already for individuals, or
Which one is, for example? Sorry.
we had looked, I think, at like QM9
Oh
or
yeah.
protein databases.
Yeah, so if some of you are working on biology, so there's a lot of so there's OGB, for example, which is very popular benchmark in graphs, and they provide a lot of data. I mean, graph level. So if you look like here, you could get node property prediction, link, graph property prediction. They even have large scale graphs or challenges. I mean, good place to start would be maybe if you want to do some link prediction would be with these data sets. They also have a leadership board with performance, the top people. Like, for example, if you go to here, you could, you see the people who are on the top. For example, these guys are maybe they have the best model on this data set. So these benchmarks provide this. There is another benchmark which has also the other data set, which was the name. The one that had QM9, right? And so yeah, so you could even find here papers with code. But there's a lot of benchmarks that basically provide these data sets. And yeah, I could share some of them later. But yeah, and for molecules, this for materials, I mean, in here at Mila, a lot of people work on materials. I think there's a big group of almost 50 people or more than work in materials, and they do have a lot of resources. So if you look into what people using GFlow nets and they are doing, these are mostly on material discovery. I think this could be a good way to look into, basically.
Well, I think nobody has a question. Well, I'd like to thank our presenters once again. I'd like to also thank Digital Research Alliance Canada for funding this initiative. And without further ado, I will end the recording.